Hey everyone, welcome to this presentation. I am Hemant Banawat. I lead the performance engineering team at Yugabyte. In this session, we'll be talking about Yugabyte DB and AWS Graviton, how we are working with Graviton, Yugabyte DB. As part of this presentation, we will first cover certain details about Graviton. How does Graviton work? What are the price performance ratio with Graviton, some benefits with Graviton? That is what we would be discussing as first part. Then we will talk about Yugabyte DB and Graviton, primarily from a performance perspective. These are the two things that we are going to cover during this session. And finally, a set of next steps that we plan to have with the AWS team as well. So yeah, I think I've already told about myself. I'm Hemant Banawat, and with me there will be Arthur. Arthur, who is a principal solution architect with AWS. He will be covering the Graviton part of it. So over to you, Arthur, if you would like to introduce yourself and talk about, a little bit about Graviton.
Thanks a lot, Hemant. So I'm Arthur Petit-Pierre, principal engineer at AWS, focusing mainly on Graviton-based instances and helping customers and partners to adopt them. Can you switch to the next slide? And we will start talking a little bit about the Graviton processors, how we designed it at AWS, and how customers can benefit from them. Can you switch to the next one? Okay, and can you please show it entirely? Well, one more, awesome. So the Graviton processors or custom design processors that we've built at AWS, the full design has been done by an AWS team. We are at the third generation now. We've announced the Graviton 3 a couple months ago, and we are slowly ramping them up. The processor that we will mainly talk about today with Yugabyte folks is the Graviton 2. That one is in full production. It's available in 23 regions with many different instance types. So definitely the one that you can use everywhere and for which you can benefit from the performance everywhere. Those processors, as I said, are all custom AWS silicon based on the 64-bit ARM architecture. We've optimized them with specifically cloud workloads in mind, which means that we chose a size with 64 cores that was a good fit to build our virtual machine on top and offer that to customers. And one of the major reason why we've chosen to add that new range of processors on top of the existing x86 processors that we had in our portfolio since many years is that having our own brand of processor allows us to rapidly innovate, build, and iterate on behalf of our customers. So anytime we receive a piece of feedback about one specific feature that the processor can be improved, that's a feedback we collect and on which we build the next version of the processor. Can you switch to the next one, please? Awesome, and let's build that one. Okay, that's going to be perfect. So thank you. Well, one back. The Graviton processor, the Graviton 2 processor is based on an ARM Neoverse N1 design. So we've collaborated extensively with the ARM folks to build the Neoverse N1. It's based on the 8.2 version of the ARM architecture. And yeah, we've collaborated closely with ARM on that one to build a processor that would be fast in the context of cloud workloads. We were pretty much convinced that we needed a large amount of cache to make the application faster. So we have 64 kilobyte of level 1 cache dedicated to each of the cores, 1 megabyte of L2 cache, again, dedicated to each of the cores. We have a coherent instruction cache. We've worked a lot to ensure a really low overhead for interrupts and for virtualization so that we could efficiently implement virtual machines in the cloud. It has dual SIMD units. So if you have anything vectorized, you can run that on Graviton-based instances. And it also supports a couple data types that are really specific to machine learning, like int8 and FP16, that allows to reduce the size of machine learning model and make them faster. One thing really specific about that processor, contrary to the rest of the processors that we have in our portfolio, we don't implement hyperthreading, which means that every vCPU that you get on our virtual machine is a full physical core. From a scaling perspective, it has a couple of consequences, mainly the fact that when you start scaling on more than one vCPU, it scales linearly. You don't have the kind of impact that you have when using hyperthreads, where with two hyperthreads, you kind of get 1.6 to 1.8 times the performance of a single hyperthread because of the contention between the two sharing the resources. On Graviton 2, each of the vCPU is a physical core, so you really get twice the performance of a single physical core when you scale to 2 and more. Next slide, please, Eamon. On that processor, we have 64 cores connected together with a mesh. So they are all close together with a 2 terabyte bisection bandwidth. We have 32 megabyte of last level cache on that processor. So if you include the private caches, that's more than 100 megabytes of user accessible caches on that processor. The memory topology is pretty much flat, so you don't have any NUMA concern from a development perspective. Wherever you allocate the memory, it will be at the same distance, so you get the same bandwidth and the same latency. You don't have the problem of having to access a remote node and have a reduced bandwidth and a higher latency. That one is pretty much flat, so that's pretty convenient, particularly for databases. And we have lots of PCI Express lines to make it pretty extensible and do a lot of I/O. Can you switch to the next one? Awesome. In terms of portfolio, we now have a pretty large Graviton 2-based portfolio. So we cover our C, M, and R family, which are our general purpose instances, with memory going from 2 gigabyte per vCPU on the C class up to 8 gigabyte of memory for the R class. We even have a specific family for really, really high memory, the X2GD. That's the same processor, but can go up to 1 terabyte of memory. We have our T4G class, which is the burstable type of instances, so the equivalent with a Graviton processor to what you were potentially used to use with our T3 or T3A instances. And we've recently introduced IM4GN and IS4GEN, and here I'm totally sorry about the name, but I'm not sorry about the storage performance of those storage-specific instances. They are utilizing our Nitro SSDs, which are another piece of silicon designed by AWS that has been specifically optimized with a pretty consistent latency on when doing I/Os on those SSDs. We also have the G5G. The G5G is our first version of a Graviton-based instance with a GPU. It has a T4G NVIDIA GPU, so pretty convenient and pretty cost-effective if you have any kind of application that would do application streaming, potentially with Android, or any kind of graphical rendering. And it's also a good fit for AI and ML types of workload that requires a GPU. Next slide, please. Thank you. From a TCO perspective, the Graviton 2-based instances tend to offer the best level of performance in our portfolio in their instance family. They're 20% lower costs compared to the equivalent instances using x86 processors in the same generation. and they can be up to 40% better from a price performance. So you may ask, where's that 40% coming from? So it's a combination of the 20% lower cost on the on-demand price. So for example, if you compare a C5 in a given size, let's say a C5 4XL to a C6G 4XL, so one is an x86 processor, the other one is a Graviton one, the Graviton is going to be 20% cheaper. And that's the same for each and every size, the same for each and every family. So you have that 20% and you always get it. The second part is the performance gain that you may or may not have, depending on how much optimized your application has been for the ARM64 architecture. And here we've seen customers seeing results from anywhere between 0 and 60% better performance. If you get 0, please let us know. There's probably some work that we can do with you to improve the performance. We've collaborated with the Yugabyte guys and got some gain. There's still more to get, but we will get there. And if you get 60%, well, awesome, you've done an awesome job and you're most probably benefiting a lot from those processors. On average, we tend to see somewhere around 20 to 30%, and that's the reason why we claim that 40% better price performance. Can you switch to the next one? Thank you. Oh, well, one more. Awesome. We've just announced the third generation of the Graviton processor. So today we have our first family based on the Graviton 3. It's called the C7G. It's significantly faster than instances based on the Graviton 2 processor. So for single-threaded generic kind of workloads, it's up to 20%, 25% faster compared to Graviton 2. For some specific workloads like vectorized floating point type of workloads like HPC or any kind of high performance simulation type of workload using mathematical primitives, it can be up to twice faster because we doubled the size of the vectors that the Graviton 3 can use. It's also twice faster for some crypto-related workloads. We've doubled the number of 64-bit integer multipliers that is used for some crypto algorithm. And it's up to 3 times better for machine learning performance compared to Graviton 2. The reason for that is first, the fact that we can do twice the number of floating point operations thanks to the bigger vectors, and also because we've added a data type that allows to make the machine learning model smaller, so it uses less of the memory bandwidth and makes it faster. It's also the first instance in the cloud to feature DDR5, which has a 50% better bandwidth compared to DDR4. And from an energy standpoint, it's 60% more efficient than comparable EC2 instances in our portfolio. Today, they provide the best price performance for compute-intensive workloads in Amazon EC2. We have made them available in a couple regions for now. You will see us announcing more region in the very short-term future, and Emmett will tell you more about their plans to also test on Graviton 3-based instances. Thank you, Emmett. Over to you.
Thanks for a great walkthrough of Graviton and its performance. So for the rest of the presentation, I will be primarily talking about Yugabyte DB on Graviton. And like I said, it will be primarily from a performance perspective. So yeah, let's start with it. So when we started with Yugabyte DB and we started using Graviton, the first thing we had to obviously do was to build on Graviton. For building on Graviton and for enabling the ARM architecture specific features with our GCC compiler, we had just to use a flag which was ARM v8.2-A. So this basically enables all the ARM features. Graviton 2 processors have support for large system extensions, which are basically low-cost atomic operations, which improve system throughput, right? So just with the flag ARMv 8.2, the large system extensions are also enabled, and the builds can take benefit of those things. Yeah, so once we had a build on Graviton, the next thing was obviously to check the performance of Graviton versus the earlier instances that we were using regularly. So we started benchmarking Intel versus Graviton instances. We had a 3-node Yugabyte universe, wherein we were using C5 instances for Intel. These are second generation Intel Xeon scalable processors, and we were using C6G instances for Graviton, which is Graviton 2. For them, we used 16 core boxes with 32 GB of RAM, which are 4XL size boxes. And the Linux distribution that we were using was CentOS 8. And then we were running a read workload as well as a write workload. The read workload is basically firing a bunch of select statements from a tool called Sysbench. Sysbench is a pretty standard tool in the OLTP world. So, and Sysbench has these standard read and write workloads, which we were using to run these workloads. In the graphs, you can see the left side is a throughput graph, while the right side is a latency graph. I will maintain the same consistency across the presentation. So the left side is a throughput and right side is latency. Higher the throughput, better it is. Lower the latency, better it is. If you see, there is read workloads. We have numbers for both read workloads and write workloads. Read 120 indicates that the read workload was run with 120 threads. Read 240 means read workload was running with concurrent 240 threads, and same for write workloads, which was run with 48 threads, 96 threads, and 120 threads, right? So now, if you compare Intel, which is the blue bars, versus the Graviton, which is the red bar, you can see that Intel was performing very nicely both on throughput as well as on the latency aspect. This came as a surprise because we were hoping that it will be somewhere closer to Graviton would be somewhere closer to Intel, but it was like far away. So we went into debugging mode, just tried to figure out what is happening, and what we found was this, right? On Intel machines, which is the left side graphs of disk IOPS and right side is the Graviton graphs. So in the Intel graphs, as you can see, we were doing about 6,000 IOPS, and the bandwidth, the disk bandwidth that we was consuming was around 120 Mbps, around that number. So which means is that we were about doing 20 kbps for every disk IOP. So every disk IOP on an average was doing 20 kbps. While if you see in Graviton for 6,000 IOPS, we were about doing around maybe 450 or 500 Mbps, right? So which means every disk IOP which we were doing on Graviton boxes was consuming about 80 to 100 kbps, right? Which was causing 80 to 100 kbps of read from the disk. What was happening was that because of this, the disk bandwidth was getting exhausted because the AWS disks have a upper disk bandwidth, which we had set to certain number, and it was getting exhausted. And once it was getting exhausted, all the reads and writes were throttled, and we were seeing worse performance. So we were just looking for reasons why we are reading much more in case of Graviton, and it turned out that when you run a benchmark on Intel plus CentOS, the OS page size is about 4 KB. Not about, it's 4 KB. While when you run while on Graviton plus CentOS, it is 64 KB. This was surprising because on Ubuntu and Amazon Linux too, this was not the case. On those boxes also, Graviton had 4K box sizes, 4K page sizes. And even CentOS 8, which has this 64K of page size, has in its recent build reverted it back to 4K sizes, right? So Graviton plus CentOS 9 might not see this problem because there you might have a page size of 4K, right? So this was problem which was very specific to Graviton plus CentOS 8, which resulted in a very high disk bandwidth. And the obvious resolution to it was that let's move to a different OS, because at that point when we were doing this thing, the latest release of CentOS or Alma Linux were not available. They were with 4K, with 64K page size only. So we moved to Ubuntu and Amazon Linux 2 for our further testing. Now, when hold on, I missed a slide. Yeah. Then we ran again certain tests. These tests were Ubuntu and Amazon Linux 2. Same test, it was run with read 120, 240, 480 threads, write 48, 96, and 120 threads. The same tests were run, but the numbers improved. Definitely the numbers improved. And also we stopped hitting the disk limits that we were hitting earlier with Ubuntu and Amazon Linux 2, but they were not still in the range that we were expecting them to be. They were still lower. The write was much lower. Even the read in certain scenarios was also less, right? So again, we just debugged it, saw what the problem was, and we reached out to AWS team, which were helpful in asking a bunch of questions and giving us a lot of different areas to target for. And what we figured out was that the Yugabyte build uses C-lang link time optimization, which improves the performance boost in the range of 20 to 30%, right? And these were being used for the Intel builds, for the Intel plus CentOS builds, while it was not being used for the Graviton builds. And once we enabled the LTO for Graviton builds, we started seeing pretty good performance, right? The performance improved significantly. Yeah. So these are the numbers after we did it. If you can see, the read workload is pretty good now. We are achieving what, I mean, with Graviton, we are achieving the similar numbers that we are achieving with Intel. So the throughput is pretty good. The latencies are also a bit inside, but that is expected with Graviton, the architecture of Graviton. So yeah, that is okay. The still one problem that remains from Yugabyte perspective is the write workload, and that is where Arthur and his team are working with us, and we are trying to see what are the different things that we can optimize so that we can get better performance of write as well, right? So from this graph, I think this gave us a confidence. This primary test was C54.xl and C6G.4xl instances, which we were testing, like I explained earlier. So yeah, I think these numbers were pretty good, encouraging, and that is where I think we started discussing whether we can move Yugabyte cloud instances to Graviton, right? That is the discussion that started internally in the team, and that is why we wanted to run certain tests on Yugabyte cloud instances. I mean, the instance type that we use in the cloud. As a first step, we want to move Yugabyte's free tier cloud to Graviton. All the instances that are running in free tier, we want them to move to Graviton. They are for free tier, we use burstable instances, which are T3.medium as of today. And like Arthur said, an equivalent for T3.medium, which is an Intel instance, the equivalent is T4G.medium instance, which is a Graviton instance. So we started comparing these burstable instances. Obviously, for free tier, normally we use burstable, because the workload is not sustained there. So when we compared T3 medium versus T4G medium, the results were pretty good. I mean, the read workload was more or less similar. With the write workloads, we were doing better. The latencies were also in the same range where we expected them to be, right? So these are pretty encouraging results from Graviton perspective and from Graviton and Yugabyte perspective. And this is what we were trying for. So yeah, I think we are where we wanted to be at the beginning of this exercise. Now, but still there is a lot of work to do from our end, and we would continue to invest in this side of the things. The next steps with Yugabyte DB and Graviton, from our perspective, is that we, like I said, since the performance numbers are really encouraging, we want to move Yugabyte DB managed, which is the cloud offering, our cloud offering, to T4G instance type. It's free tier to T4G instance type. We will also work with Arthur and his team to improve the write throughput on C6G instances, which is a slightly less than Intel instances, but we will work through them. And we would also like to try Graviton 3 instances, which has a better price performance ratio as compared to Graviton 2. So we'll definitely like to go there with Graviton 3 instances, and that is what we would like to try. So yeah, I think that is what I wanted to cover. We just walked you through the complete journey we had with Yugabyte and Graviton. Thank you for your time, and we are here for any questions that you might have.